I'm coming from San Diego. It is surprisingly hotter here than there, and I'm wearing black, but it is what it is. Um, so I'm going to talk to you about JavaScript engines, and in particular finding bugs in these runtime systems, and kind of a new API for how to actually address these bugs. This is joint work with a bunch of folks at UCSD. One of them is over there, so you should hunt him down, Ranjit, and a bunch of folks at Stanford. I don't think any of them are here, unfortunately. Okay, so let's talk a little bit about JavaScript. So unfortunately, everything runs JavaScript now. So it's no longer just browsers. Your web server is running JavaScript. Your desktop app, your Spotify, Slack, and whatever you're using, it's running JavaScript. Your devices that are measuring temperature and maybe something more important than temperature are running JavaScript. Even satellites are running JavaScript, and that should be scary. But it's also pretty cool, and one of the reasons it's cool is because it's super easy to run JavaScript on all these platforms and devices. So here, I hope you can't read the code, but and I hope you trust when I say it's 62 lines, but actually 49 SLOCs. So in 49 lines, you can use V8, Google's V8 JavaScript engine, and you can now have your application run JavaScript as well. So you can start writing your applications in a way that they're crash safe, so your program won't actually segfault. They're type safe, right? So like in JavaScript, you can't misuse or have out of bounds arrays. It's also memory safe. So these are all super awesome things that we like and we love from high-level languages that we don't get from C and C++. Kind of, right? JavaScript alone is not actually giving you much. It's completely useless, actually, unless what you're trying to do is build a heater, which you might be nowadays because it's an IoT thing. And in practice, what we actually do is we have this thing called binding code that makes JavaScript useful, right? So JavaScript has no way of performing I/O. In fact, it's defined by the ECMAScript, and the only thing it can do is have super simple programming constructs like loops and so forth, and it has mutable arrays, but other than that, it can't, say, talk directly to the network. It can't read a file. It can't do anything that you might want to do in a real program, right? So in order to do all those things, what you do is, as the thing that's embedding the JavaScript engine, you extend the JavaScript environment with this thing called binding code to expose this low-level functionality, this functionality that we have in C and C++, to do useful things, right? So for example, on the server side for Node.js, one thing you might do is expose the file system. And this is what the FS library does. Or you might expose, say, net, the ability to talk to network devices. Or, say, access OpenSSL with crypto library. And the browser side, which is something that you might be more familiar with, well, DOM, that's one example of a useful API that we extend the JavaScript runtime with, right? So we extend it in a way that we can modify pages and elements on the pages and render them and so forth. Similarly, we have the XML HTTP request API, right? This lets you talk to remote servers, and now we have web workers and a bunch of other really awesome new things. But all these things aren't baked into the language. In part, that's good, but it also means that we have to extend these languages with C code. Okay, so let's talk a little bit about like what binding code actually is, right? So binding code lets us do useful things, and the way it does that is by exposing new functions or objects as prototypes on existing JavaScript objects, like say the global object, and when you say call one of these functions, it calls into the C++ layer, and the C++ function there can actually, say, talk to the network after, say, looking at your argument to modify different properties of the object that you call this function with, right? So if we were to have, say, a diagram explaining what binding code looks like, well, you have the JavaScript app code running at the top, and this thing talks to some C++ code in the binding layer, which itself is written in the JavaScript runtime system that has this V8 API for manipulating, say, JavaScript objects and talking to the network. So let's look at an actual example of binding code. Let's suppose that the thing that we want to do is write a file to, write a string to a file, right? So JavaScript doesn't let us do this, and we're going to use binding code to expose this. So here I've broken down my slide into two parts. One is the JavaScript side, that's the top, and then the bottom is C++. So in C++, let's pretend we have a function called writeFile. You can imagine using IOStream or something like that instead. And this thing takes a string and a file name, right? So it writes that string to whatever that file path is. So this is all pure C++. and the binding layer code comes around it. So it wraps the C++ code to expose it to JavaScript. So what is this code actually doing? Can you guys actually see this? If you can't, I'm totally screwed. Ish? Okay, let's go with ish. Okay, so this is using the V8 API, but there are other APIs like Mozilla, SpiderMonkey that you can use instead. So what this function is doing is it's taking, say, JavaScript arguments, and these are all of one type. This is the function callback info value. So they're all values. They're all treated as one single type. Internally, they might be, say, strings. And the first thing that we do in this function is look at argument 0 and argument 1 and treat them both as strings. So we cast them to these string types, and now we have these strings that we can then use in our write file C++ function to actually write the string to the file path. Now this is a binding function, and you would use the V8 API to expose this function to JavaScript. The way you do this is you take, say, the global object, and you set a property on it called write to file, and give it the function that you want to expose to JavaScript. And now in JavaScript, we have this function that's on the global object that we can just call as we normally would by just passing it JavaScript strings, and then these whole things just trickle down into our actual write file implementation. Okay, so we have JavaScript code that now calls into C++, and of course, C++ is not safe like JavaScript is, and binding code introduces the same old problems that we had in C++, like use after freeze or out of bounds reads and writes to JavaScript code, right? So this happens all the time, and the reason for it is because you have to really battle these three things when you're writing this binding code, right? You have to preserve JavaScript crash safety, right? JavaScript doesn't segfault, so when you write this binding layer function, you need to make sure that it's not actually hard crashing. And what that usually means is if there's a failure mode, you have to throw an exception back to JavaScript. Now, the V8 API that you'd have to use to actually do this is pretty gnarly because you're managing basically JavaScript control flow in a C++ language that doesn't actually, where you normally would not use exceptions. Similarly, we'd have to manage type safety, right? Whenever we actually use one of these JavaScript values, we actually have to check its type, and before we use it, make sure that it's the type that we expect it to be. And of course, when we're actually using, say, a pointer, we have to make sure that this pointer actually points to a live object when we use it, even though the binding code function itself might go back and forth between JavaScript and C++ land. And of course, real code doesn't actually do this all the time, right? Like, what this means is that we now have the same class of bugs that we have in C and C++ that are now introduced to JavaScript code, which, you know, by construction should not have actually been there. And the whole point for like using one of these languages is that it prevents you from shooting yourself in the face with things that we're scared to use in C++. And right, like, you don't expect as much from a JavaScript developer as you would from, say, a C++ developer. So it's slightly even scarier than it normally is. Okay, and the context that we've been looking at is basically of untrusted code, right? Like now you have this untrusted JavaScript code that's running, say, in the browser. This code might be, say, a JavaScript add, right? This add might call into the binding layer through, say, the DOM API, which calls the binding layer function, and of course might make your tab very sad. Now this is, say, just a form of a crash, but crashes do actually matter themselves, right? So if you're talking about web servers, I can now take down your web server, but always crashing your process. Maybe more scary is that these things are running on like hardware now and exposing hardware, so I can potentially take down your IoT system or your satellite. So crash safety, like in the browser, might not matter because the browser people have actually thought about this for a while, but in other settings, it starts to matter. Type safety, on the other hand, still matters in the browsers, and it matters in both, say, Chrome and PDFum, and even Chrome extensions. And the reason for it is because you might be able to execute arbitrary code. So if you can execute arbitrary code, I could potentially steal, say, your tax document that lives in a different PDF, or I can bypass the same origin policy and read your banking information. And the same goes with memory safety bugs, right? So out of bounds reads and writes and use after freeze, these are really serious problems. And, you know, the least that you can do is on a server, say, leak SSL keys, or you can, in the browser, bypass the same origin policy by just simply setting a bit. And of course, you can start now executing arbitrary code as well, depending on what kind of bug we're talking about. Okay, so these bugs can have security implications, and if you're curious about the particular ones and the runtime systems we looked at, I'd be happy to talk to you about that. But the thing that I want to maybe hammer on a bit more is that these bugs are super easy to actually introduce in real code. And this is because it's easier to hard crash in your C++ binding code than it is to, say, handle an exception and throw it back to JavaScript, right? Like, you're now having to mix and match JavaScript control flow in the C++ binding code. And similarly, it's easier to just cast a JavaScript value to primitives, to objects, and so forth without actually checking the type first. If you check the type and it has the wrong type, what do you have to do? You have to throw an exception back to JavaScript. Why would you do that when you can just cast? And maybe worst of all is that you can really use these APIs to shoot yourself in the foot by calling back into JavaScript. And you do so because this control flow is not actually made explicit, right? And once you call back into JavaScript, if this JavaScript is controlled by an attacker, well, it might violate the invariants that you've set up in this binding function about, say, C++ data types. And as a result, say, on a reentry into C++ land, you might be reading or touching an object that's no longer live. But you don't have to kind of trust me. I think like the people that you might want to trust more are the Chrome developers that have looked at this binding code for quite some time. And their summary of it is basically that it's just super hacks. And it's so gnarly that they've gone through the effort of implementing a garbage collector in C++ not to actually worry about memory safety and Chrome down binding code. But not everybody has the same amount of money as Google, so people are still managing memory manually and getting into trouble with that. Okay, and I want to tell you a little bit about those people, I guess. So what we did was we started looking at binding code really hard, and then we're like, okay, can we actually write static checkers that will find these bugs for us? And I'm going to talk to you about a few of these static analysis that are super hacky, but nevertheless find real bugs in real code. We've looked at 4 different systems. Node.js, which is the server-side framework, but it's also used now on all these other devices. PDFum, so that's your Chrome PDF renderer that, if you didn't know, it actually runs JavaScript because PDFs, as it does everything else, it runs JavaScript. And the Chrome extension system, which itself has a bunch of binding code to actually let you manipulate, say, tabs, pages, network requests, and so forth. And Blink. So Blink is Chrome's rendering engine. That's the thing that actually gives you, say, the DOM object. Okay, so I'm going to talk to you about the static analysis tools, and then a new binding API that addresses the problems that are inherent to the V8 API. I'm only going to talk to you about 2 systems in this talk. If you're interested about the other systems, we have a paper on this. You can check out bindings.programming.systems, but I'm also happy to talk to you about it after the talk. Okay, so let's talk about some static analysis. This is the pipeline that you are all familiar with. So we are basically taking a super simple static analysis framework that takes a bunch of code, parses it, gives you tokens, and then creates an AST that we then check for particular patterns that we've come up with after looking at a bunch of CVEs, basically. But it basically comes down to like all these 3 different violations, right? Crash safety, type safety, and memory safety at the boundaries where you cross between JavaScript and C++. Now, the specific tool that we're using is called µchex, and it's really just meant for finding these kinds of bugs. It's not sound at all. In fact, it only parses a subset of C++ and a subset of these idioms, right? So between Node.js, PDFum, Blink, and Chrome extension system, they all have wrappers around the V8 engine, and we basically want to focus on finding patterns that are specific to those systems as opposed to having a very sound and precise and general static analysis tool that would make it kind of harder to actually figure out like what these bugs look like. And these checkers target, again, the 3 things. So one is hard crashes. So we basically look to see when are you using a hard crashing API, or when do you have an assert that you probably shouldn't have an assert that can be triggered by JavaScript code. We also check for type confusion. So when do you actually use a value without checking its type? So when do you do casting? And of course, out of bounds reason rights. And finally, some use after freeze in the context of the PDFum API. Now, overall, we've flagged roughly 155 bugs, but we didn't confirm all of these. We only looked for 81, mostly because we were lazy, and I need to maybe spend the rest of this week in Barcelona on the others. But anyway, we still actually found like 81 confirmed bugs, and a bunch of these are actually pretty serious. So let me talk to you a little bit about those bugs. Okay. So what do they actually look like? Well, here is an example of a Node.js binding layer function. This function is part of the core library, part of the core buffer library, which is basically as core as you can get. And this function fills a buffer with a from 0 to 10. Internally, this function basically takes those two arguments, treats them as integers, computes the length of the thing to fill, and then calls memcopy to actually fill the buffer with the values that you want it to fill. Now, there are no checks that are actually really performed in C++ land. So what this means is that if we can call this function directly from JavaScript with eval values for start and end, then we can perform an arbitrary memory write to memory, right? So if we can control the start and end, we can just set it to eval values, and then the memcopy will do whatever we want it to do, right? So this is pretty standard. So this is what the exploit actually looks like. And in fact, you could call this function directly in Node. But Node doesn't want you to use this function directly. So Node actually has wraps the binding layer with a thin JavaScript layer. And this is actually a really good idea, and it's an idea I think that they might have borrowed from the Chrome extension system. And the basic idea is like, hey, like we're going to write as little C++ as possible, write the rest of the core libraries in JavaScript because JavaScript is safe, so we don't have to necessarily worry about bugs that happen in C++ land. The problem is that in practice, they didn't really do a good job of isolating this JavaScript, this binding layer from it being accessible to arbitrary code. So you can call these binding functions directly, and what's worse is because they have this thin layer of JavaScript that checks and performs, like say, things like bounds checks, they didn't do these checks in C++ as well, so it's not actually defensive. So their actual binding layer functions are not defensive, and they're still directly accessible. And most of the time, you can really like get at executing these binding layer functions directly. But like we can pretend that one day they'll actually hide these binding layer functions, and the only thing that we can actually touch are the exposed Node libraries. And given that, we want to actually still trigger that previous buffer fill example. And this is kind of like the thing that we went through after finding these binding layer functions is how can we actually trigger them from the core exposed API. Okay, so to go through that, I'm going to take the buffer fill example again and show you what it's like and what it's actually doing internally. So when you call buff fill, this will call the buffer.prototype.fill function. And this function basically has a JavaScript function that performs the bounds check. And after it performs the bounds check, it calls the binding layer fill function that we saw before. Yeah? So this is basically what it's doing. It's just passing through if everything is good. But if everything is not good, then the bounds check in JavaScript would throw an exception, for example. Now, how do we actually bypass and get this exploit working? Well, the thing that we need to do is make sure that we pass the JavaScript bounds check. So when we call bounds check with start and end, we want to make sure that like it says, yeah, good to go. It doesn't throw an exception. But we still want to, when we get to the C++ binding layer function, actually give it two eval values for start and end so we can perform our arbitrary memory write. So how can we actually do this? Well, we're going to leverage the fact that JavaScript has a bunch of really crazy and awesome features. So one of the things you can do is you can override the implicit casting function definition, which given an object would say convert it to a primitive. So in this case, I have one object called obj, and when you use this object as an int, it will call my function here that will do quack, 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 and then give you 55. Yeah? And internally, this uint32 function that we saw before, well, it will actually call such a user-defined function when given an object like this. It won't say automatically give you a 0 as the old version of JavaScript used to do. So what this means is that now we can call bufffill with these two objects, and our two objects just do evil things. In particular, what they do is the first time around, they give you start values of 0 and 10, but the next time around, do our evil, say, values of -1 and maybe 10. And that allows us to get to memcopy directly and write any part of memory that we want. So what should they have done? Well, they really should have type checked in JavaScript and probably C++. But okay, that's what it is. I want to tell you how we've kind of generalized this and what the actual static checkers look for in our system. So the idea is actually pretty simple, as I think you can imagine from what you just saw, which is like once you have user JavaScript that can influence values, if these values actually influence, say, a memcopy or any other dangerous operation, we're going to flag it and then go back and inspect it and see if we can trigger this bug directly. So what we're basically doing internally in the checker, we're keeping track of two things. One is the unchecked types, And these are values that come from JavaScript that you might not have yet checked. And then for each of these values that end up being in this unchecked type set, when you use them in a, say, memcopy operation, we then flag. Okay, so going through our fill function, what our checker does is it immediately, upon entry, says like, hey, args is something that's coming from JavaScript land. Let's add it into the unchecked types because you haven't looked at any of the arguments. Then we go through the function body, and one thing that we see is that we're using args2 as a uint32 value, right? So we're adding start to our potentially dangerous values, and we're doing the same thing for end. And then once we actually get to the memcopy, we see that start is actually in the dangerous value set, and we flag this as a bug. Now, this is not always going to be a bug, because sometimes you can't actually trigger from JavaScript these C++ functions, but most of the time, at least in Node, they do manifest as real bugs. But Node is not the only one that's doing the wrong thing here. PDFum is another example that has a bunch of bugs that we've managed to flag. And here's one example of a use after free in PDFum. Now, what the checker does for PDFum is it flags any pointer if this pointer, say, was allocated in a function, or pointing to an object in a function that lives in JavaScript land, and then after that you have a call into JavaScript that might have actually freed that pointer, and then this pointer is used again. So to give you a concrete example, here's the annotation name function, and here what we have is this CJS prop value, so you don't actually need to understand any of these types, but the thing to understand is that this is a user supplied value, the same things as we had before with a function callback args. Okay, so when we enter the function, what do we have? Well, we have a pointer to this annotation. This annotation is a C++ pointer, but it's actually backed, it's backing a JavaScript object. So what this means is when we hit this line here, VP greater than inode name, well, we can potentially free this pointer. And the reason for it is because this greater than operator, the PDFing guys have, well, overloaded it to call into JavaScript. What it actually does is it calls toString internally, and toString you can always redefine. And within the toString function, if we're malicious, we can force a garbage collection of the previous object, and then when we get to the next line and still use that pointer, well, this will be an invalid pointer, and if we've had just the right alignments, we can get it to execute arbitrary code for us. Okay, so that particular bounty, that particular bug, like Chrome actually recognized as a problem, and it's one of the few ones that we reported, and I guess it's a signal that they actually do care about these kinds of use after freeze. But of the others, of the 81 bugs that we confirmed, they roughly break down into mostly crash safety, so the roughly 70 crash safety bugs, and then a few type safety and memory safety violations. Now I want to point out that these are bugs in runtime systems, right? They're not bugs in applications, and what that means is that all the applications running on top of these runtimes are vulnerable to these kinds of attacks. So you can take down a server pretty easily with Node. And the thing that I want to kind of highlight a little bit more is, well, who are we to blame here? Is it Node and PDFum for misusing the V8 API or not writing safe code, or is it somebody else? My take is that, well, the binding API design itself is what's at flaw, and here's, I guess, some fake evidence to support that claim. The first one is, well, if we look at like what we've actually flagged, well, we've managed to flag most of Node's core libraries. So pretty much if you take a Node core library, you can get it to crash. In fact, you could get it to crash even when Node runs on Chakra Core, which is a different V8. Well, it's a different engine, but it basically provides a V8-like interface, at least for Node. And similarly for PDFum, we've managed to crash most of the APIs that they expose to JavaScript as well, right? So that means that people are seriously misusing these APIs, and we need to rethink how these APIs are presented to developers. And this is exactly what we did, right? So we designed a new binding layer API that helps us prevent these kinds of bugs by construction. And we're calling this Safe V8. So Safe V8 is actually just a wrapper around V8, but you can imagine implementing it directly above the JavaScript VM as opposed to what we did. And the three kind of takeaways that we wanted to instill in this API design was like, well, one, let's force developers to actually handle errors, right? So there are a lot of crash safety violations. Well, let's make sure that whenever you call into the binding layer, you're not actually allowing developers to easily hard crash. That means our API should not let you easily crash, right? So we're not exposing any function that hard crashes and gives you a way out that's easier than handling the exception. Similarly, let's not actually allow developers to use values without first checking types. So our API only provides these primitives for marshalling values from JavaScript to C++ land after you've actually performed a type check. And finally, to address memory safety concerns, let's make sure that every time you cross the language boundary, this is explicit, and this forces you to actually think about the invariants that might be violated as a result of a call to JavaScript. Okay, so given those constraints, this is what the fill function I've showed you before looks like with safe V8. So we didn't want to change the semantics of the fill function, and in this case, a implicit cast actually still calls back into JavaScript, but it does it assuming that you get back a uint32. And if you don't, then you should handle the exception and actually just throw back to JavaScript. And similarly, we do for the second argument, and so forth. Now, you might be looking at this and it just looks like callback hell, and that's actually intentional. And this is meant to look like JavaScript because when you're writing binding code, you're essentially writing JavaScript code but using C++ APIs. So write what you intend to write, not this ugly, broken thing. Granted, callbacks are ugly too, but that's a separate conversation. Okay, so we've implemented this, and how do we actually evaluate it? Well, we had basically three things in mind. One is, can we actually still implement everything that V8 implements? And in order to test this, we just ported all of Node to our safe binding API. And in fact, we've managed to do that with partially having a tool rewrite the code for us. So we've rewritten all of Node's binding layer with this API, and we've ran their tests to actually check for compatibility, right? We don't want to change the semantics except for, say, crash safety and things like that. So to confirm that, we ran the test, passed all of Node's tests, and in fact, we ran all of Node's regression tests, which includes running basically packages from the Node package manager, just taking those packages and running those tests. So it's like roughly 74 packages, but you can imagine going crazier and taking more packages from NPM and running those tests. And in that case, we also passed the test. So that's compatibility and expressiveness. The other one was performance. Of course, like if this thing is super slow, there's no point in ever actually using it. And we've ran, again, Node's regression tests here, and the performance measurements are on average negligible. The max was at around 11%, but these are micro benchmarks, not necessarily super meaningful. In order to test something more meaningful, we ran a bunch of real-world benchmarks. Maybe the most notable one is Express.js, which is a web server, and we measured its performance to be less than 1%. Okay, so that's Safe V8, and we're still working on this project. There are a few things that we're kind of trying to tackle. One is, can we automatically generate exploits across these languages, right? So we've looked at 81 bugs out of the 155 that we flagged. Well, the question is, can we take the rest, like 70 or whatever they are, and actually do that automatically, or have a way of signaling that this is actually not triggable from JavaScript land? But beyond that, we also want to look at other platforms, right? So there are a lot of V8 platforms. One of them is Electron, which takes basically Chromium and Node.js and gives you a way of building desktop applications. So that makes it also interesting is, can we look at Electron and see like what kind of problems arise there at the binding layer? Or these IoT devices that are exposing hardware directly to JavaScript, like what kind of binding layer problems arise there? Or what kind of binding layer problems arise in things like NAN, which is a wrapper around V8, yet again, but is widely used by mostly third-party packages in the Node ecosystem. And of course, we can take other binding layer APIs and look at those as well. So looking at Firefox, Servo, even JavaScript would be super interesting and something that we have on the roadmap. So that's kind of looking at the checker side. On the Safe V8 API side, we're looking at automatically rewriting this on safe code. So we've already done part of that, but we want to show that when you do the rewriting, it actually preserves semantics and gives you correctness. And kind of part of that effort is also formalizing these multi-language systems and actually looking at this API from a formal lens. Okay, so with that, I guess I've talked to you about super simple but and system-specific checkers that found violations, and three core things three core things when it comes to safety. One is crash, the other one is type, and the third one is memory safety in these JavaScript runtimes. And I've presented a fast, backwards compatible API that ideally addresses these things. But there's a lot more to do. Like one of the things that I think is like interesting about this work is that it hasn't really been touched by the academic community. It's largely been work done in industry by Google and Mozilla. So I think like actually trying to connect with these people and figuring out how we can help as academics would be super interesting. So with that, take any questions.
Okay, thank you. So if you have questions, please come to the microphone in the middle, and we have space for a couple.
So, as you know, maybe there is a current release, Node 8. They standardized Node and API, and probably it seems like it's the very close work to what you're doing, because like it's a way to standardize writing C extensions for Node.js. Have you touched, like, communicated with them, like with the committee, Node committee or something like that? Because it seems like it's a lot of work now in that field from the official Node team.
There is. So like we've been dealing with it from the security kind of work group, largely, not from the standardization process there. But I think it'd be interesting. I don't know if they're actually dealing necessarily with these safety concerns, largely because I think it's easier not to. But yeah, I think we should probably actually touch up with them. So.
Yeah, they are like working on mostly on compatibility between versions and V8. But it would be nice, of course, to see security mitigation things.
Yeah, it would be super awesome. So actually, like the fact that our thing like worked on Chakra was a surprise to us, and the reason it worked is because Chakra basically implemented this V8-like wrapper on top of Chakra, and that's a totally different VM. And if you standardize this thing now and it's broken, it would be like maybe even worse. So yeah, I think we should do that.
Okay, so if there are no more questions, let's thank the speaker. Let's thank the speaker again, and the next session will be here in 20 minutes.